Okay.
Yeah.
All right. Working. Okay. Well, thank you all actually for the opportunity to do this presentation. It's a new one. This specific theme and layout for the presentation is new for me, and it was the motivation to do it was really conversations that I was having with research students within the CMIT, both at Griffith and at other institutions. And I was mentioning earlier to David and to Peter that one of the mistakes that I often make is that I assume the new students who come into a PhD program somehow magically have the knowledge of the previous students that have just graduated. And that's not the case. And so a lot goes unsaid, a lot goes unstated about what we already know about how to do things well. And specifically in this domain where we're focused on musculoskeletal modeling, common problems keep cropping up. So I thought I'd take the opportunity sort of in the first half or first 70% of the presentation to tell you what are the things we've done, not just like we in the possessive, but let's say the field that has established viable pathways or pipelines to create accurate, valid, personalized musculoskeletal models. And then we'll end and say, okay, what could we do better? What does the current method not do that we're failing to do? And I'll show you some preliminary proposed work that I think has some advantages, but has some challenges. And I'd love to get your guys' feedback and opinions and thoughts about maybe how we could tackle those problems that are coming up. So we don't know each other thanks to COVID. I think on other circumstances, we would have met much more often. Our group here and vice versa. So just to give you a little bit of background, despite my accent, I was not born here or in the US or Canada. I was born in Zimbabwe, and this is Victoria Falls, which translates into English in the local name to the smoke that thunders, which I think is a fantastic name for such a powerful place. If you know anything about the history of Zimbabwe, it went downhill rather quickly after 1980. So we left and I landed first in the US with my mother's family, bounced around a little bit, and eventually settled in Ottawa, Canada. A not very notable place other than it's the federal capital. So it's a bit like Canberra, stuck between two interesting cities. And so lived there for most of my years. Why? Well, my mom's an American and my dad's a Brit. And the first equation is if you add that and divide by 2, you get a Canadian. And they're a military family, US Air Corps and armored divisions in the British Army. And this is our army. We just have a whistle, and if we have a problem, the Americans will solve it for us. So that goes the theory. Now, I was educated at the University of Ottawa for both my undergraduate and my master's. I had the great luck to be the last research student of Cord Robertson, who you guys may know from certain textbooks in biomechanics literature. He was one of Dave Winter's original PhD students in the 70s in Waterloo. So this is what it looks like in the marketing text. That's what University of Ottawa looks like. It's a bit more like this most of the year. So when you guys were saying it was cold, I was like, not really, actually. So after 20 plus years of that, I was a bit over it. And I had the great good luck to land in Australia to do a PhD with David Lloyd. At that time, was at University of Western Australia, but quickly relocated to Griffith University to set up and run a research center on musculoskeletal conditions. So I think this is a better view than the previous slide. And I've stayed. I'm a citizen now, and I have 2 Australian daughters who only know this warmth, so they can never leave. But to our academic context, so this is what we want to talk about today. So if I can move some of these screen features out of the way. I don't know if this is an axiom or an assumption, but let's say it's the first move we need to make to appreciate what we're going to do. The more a model represents the actual system or structures that we're actually trying to study, the more confidence we're going to take in its representation. Now, in pure engineered structures where you know everything, you could go the other way and retract information and see when you lose critical stuff. But we don't have the complete understanding of the human body. So we always have to be pushing to make it better, higher fidelity, more representative, because we're not in the situation of knowing all parts and we can do, abulation study or remove components. We can't do that. And it's unlikely we ever will. So this is my resting assumption, that this is inherently valuable. Now, if you haven't read this, and you might not, it's in a sort of obscure journal, you should. This is a great paper. This is work that Professor Viceconte is leading, not only himself, no doubt, but I would say he's probably the linchpin in there, pushing it forward. And in Europe, in the United States, this is taking off. To use computational models to actually do trials for the purposes of regulating devices. So no physical testing, entirely done through computational methods. And this is not just for medical devices, but this is also for pharmacology and so forth. So for cancer therapies and so forth. Because as you can imagine, you can do way more of these than you can do real trials, right? So the critical thing here is that if we want to establish a model as credible, we have to verify, we need to validate it, which I think we're doing to a certain extent, but we also need to understand the uncertainty. And I would say probably that last category is where we could use some serious improvement. Now, for the purposes of today, I'm going to talk about these three domains. The skeletal system, joint mechanisms, and muscle representation. I'm going to deliberately ignore the neural component. We will get some hands-on neural practice at the ANZORS conference. We're going to do a little workshop that involves using code, analyzing outputs, and controlling neural software like Cinemas and so forth. And I'm also going to pretend the skeletal systems and joints are rigid, which they're not. But for today, that's how I'm going to approach it. So with the concept of validation and verification and so forth in mind, what do we know about how to personalize the representation of the skeleton in the individual that we're studying? We'll focus in on just the bone for a starter. So since the advent of, I guess, computed tomography, which would be the late 70s in the US, you could, if you were industrious enough and really wanted to, get some form of medical imaging, process it digitally on a computer system, software system, and then get something like the image on the far right, which is a mesh or a digital representation of this structure. And you could do that for all the bones you wanted to study. And if they're in the correct spatial alignment, you would have a static assembly of the bones based on how the person was in the imaging space. And you would have a sort of de novo skeletal model. But as you guys probably appreciate, if you haven't, manually processing medical imaging, even CT, is laborious, and you should do it, but you don't want to keep doing it. It's a good learning experience, and if only to make you aware of how unpleasant it would to do it en masse, but also some of the challenges of automating it, right? So you say, well, we should automate it, but it's not that easy, right? So it's a good learning experience if you haven't, to segment out various tissues from CT or MRI. Now, in lieu of that, the obvious idea is to work with, say, a template. You know, the human skeletal system doesn't vary infinitely. We might imagine there's, in this case, the OpenSim model. There are others, but I'll use OpenSim because it's the software that we're using quite frequently. And in that template, we can imagine different levels of anatomical information being used to inform an adjustment, get it to match an individual. So this would be in rank of higher fidelity to lower fidelity. So you've got a very rich data set, which would be detailed medical imaging, to something a little bit less refined, but still, let's say, three-dimensional, which would be a capture of fiduciary landmarks in a mocap laboratory, or to something that reduces it basically to scalar measures, like anthropometry tables or getting out the old ruler and measuring segments. And then there's some process of adjustment that goes from the template to the individual. So right away, this is an improvement in terms of the amount of time and the demand to do this. But what about its capabilities? Does this actually work? So in OpenSim, for example, you can apply isotropic transformations to all the bodies or selected bodies. And in this case, all three dimensions will be adjusted by some factor that you apply. And it could be arbitrary or it could be derived. Likewise, you could have anisotropic but still linear transformations where different proportions or factors are applied to different dimensions. So the shape changes, but it's still a linear transformation. But, and then this latter case is what's most commonly done in what's called the scaling process in OpenSim. You use either anthropometric information or data acquired in a gate lab and apply these linear scales to an individual to adjust the dimensions at different segments of their body. And this is pretty well established. There's tutorials on it, and it's still run of the mill what's done most commonly because it's very easy to do. You can implement this programmatically and it executes in less than seconds. So it's attractive from that perspective. But main problem is no form of linear transformation is going to get you from, let's imagine your template is on the left to the right. It's just not going to happen. They're not subsets of each other. It's not going to be achieved through this approach. And if you don't care about that, it's not a problem. You know, if you want to look at arbitrary motion of the jaw and not particular individuals, this is not an issue. Likewise, if you just want to study theoretical motor control or theoretical biomechanics, you don't need it. Any one of these models would do. But if you're trying to, say, build an implant for that person, and you want to prove that it's not going to break or it's not going to tear up their muscles, you must care about this, right? You have to get the geometry right. So I think we can say safely that linear scaling is not a good option for personalization where the geometry of the bone is really important. Maybe other cases where it's okay, but if you really need to know the geometry, it's unlikely this will meet your needs. And I don't think it would meet a regulator's inspection of it either. So let's look at some complex transformations. So these are, by the name, allow you to do more than what linear transformations would let you do. So here you've got a face meshed with different types of elements and put in like a control volume. And then on the right, some type of complicated deformation is applied. And you can sort of appreciate that it's the original mesh, but contorted into a new and very different shape. Right? So you couldn't go from left to right using linear methods. And along this line, maybe the first example we'll start with is something like statistical shape modeling. Now, there's lots of people in the call, but also in the room here who've done excellent work on statistical shape modeling for different structures and for different purposes. But if you're not familiar with it, the basic idea is that if you consider a training set of shapes of one class, so let's call them pelvises or pelves, they have some similarities and they have some differences. And statistically, we can characterize what are the main ways in which they vary or are similar. The technique is not from computer graphics or from anatomy, it's from statistics. One of the rare times we get to thank them for something, but that's a bit of a gift. And there's many different numerical techniques for it, but most common is something called principal component analysis, which is a way of factorizing variation in a data set into primary modes that maximally explain the variation in shape. And why is this useful? It's a good question. And in many cases, maybe it isn't useful, but it's just popular. But what it does let you do is look at a range of available shapes from a population that represents a bone of interest. And from it, you can both characterize the primary ways in which the shape changes, but I think more importantly to this discussion, you could reconstruct novel or arbitrary bones within that shape space. So way I would think about it is, if you have done this well, you'd be able to predict the shape of a new pelvis that you haven't seen with fairly minimal information, which is attractive for us because it eliminates a lot of the cost and time involved in acquiring a lot of detailed information while still preserving our respect for getting a good shape representation. So statistical shape modeling is ubiquitously used now. MATLAB, Python, there are tools for it in pretty much any language you want to operate it in. And I'm sure you guys are using these things, but if you have questions in this domain, we're more than happy to share with what resources we do have. Maybe we can be of some help, maybe not. But this method exists and is being used. Now, these are funny old pictures. So this is the earliest evidence I can find in this technique. So another approach, which is not underpinned on a training set. Actually, I should just jump back one slide. So one other thing that potentially a drawback or limitation of this method is that if in the training phase where you create your shape model, there's not a shape or a variance that it's observed or seen, then it's going to have difficulty reconstructing that if it's present in the novel bone. So what I mean by that is if there was a really strangely shaped pelvis that you're trying to reconstruct, let's say it's fractured, let's say it's got a big lesion from a sarcoma or some type of other developmental problem, and your training set is all healthies, you're not going to be able, or you're going to struggle to reconstruct that unusual shape, even though it is a pelvis. So a classic problem, adults to children. Adult statistical shape models struggle to reconstruct children pelvises because they're not just little adults. They actually have a different shape characteristics. So that's the pros and the cons here. Free-form deformation is not based on a statistical distribution or a study of population shapes. Here is originally in a totally technical and abstract field, like of algebraic geometry and things like that. They're trying to deform, in this case, unbelievably, a bunch of cubes and balls and bend it using some type of volume control. Now, I can't imagine doing this, even in 1986, as my job. It would freak me out to get up and work 10 hours on trying to do that. But I'm glad that there's people who did that, because that technique, broadly speaking, free-form deformation, has been applied under a slightly different name to the deformation of anatomical structures. So this is an application of free-form deformation called host mesh fitting, which was developed by the team at the Auckland Bioengineering Institute. So this is from Justin Fernandez's thesis, which was supervised by Peter Hunter, who's the director there. And you can see sort of the similarities on the far left. Instead of squares and cubes and spheres, you've got a femur embedded in what they call a host mesh. In computer graphics, called a control volume. And then they want to deform the host mesh while preserving its volume such that the host values, the blue ones, match the target values, which are the red bones. And that gives you the capability to almost arbitrarily deform the bone that's inside the control mesh to match targets in a very nice way. Now, they did a bunch of other things in this process that made it useful, like the element types and a few other things. But that process can actually be used in software such as Python outside of the software that was used and developed in Auckland, and in fact can be combined with the statistical shape modeling. So to overcome some of the limitations in this statistical shape modeling, you can combine these two processes, which is something we did back in 2019. We had sparse imaging of the femur and the pelvis, not entirely on purpose. It was what we could afford in the project budget. So we had sparse imaging, and we needed a way to take slices of the bone and make the whole bone for the purposes of subsequent models. So we said, all right, what if we piece together first a statistical shape model, which will get us in the ballpark, which will get us pretty close to the real shape. And then we had focused or localized scans of the joint, the distal and the proximal end. So let's use that to further refine the bone through host mesh fitting. And we were able to get a bone shape that approximated the resolution or the in-plane resolution on the MRI. So I think it was 1 mil by 1 mil. So we were getting pretty close to what you can get out of that grade of medical imaging. So this process was deployed in the MAP client, which is a workflow manager, and the language underneath it is Python. So we're happy to share those scripts and things like that if this is useful to you guys in any way. And there are many studies, right? This was just the ones that popped into my head that have used either just this statistical shape modeling or some combination or slight variant to solve different problems, right? Predominantly lower limb, but also upper limb stuff as well. And this is in just the last few years, right? So these are ubiquitous techniques now. And I think we should, if we're not using them, we should have a good argument why we're not, rather than, oh, well, I'll just use the linear scaling because it's there. And maybe to get it off the ground and work your pipeline, but then why not? These tools are really well established, you can use them. And I think the last bit, this is not super useful for the medical implant side of things, but it's very useful for accessibility in the rehab and the sports community. So if we imagine technologies that need personalized models, but need to say use them in environments where they're not going to have a mocap system, they're not going to have, or they'll have a very primitive one, or they're not going to have medical imaging. This is really cool because, again, from ABI, here the innovation was, instead of using points on the body as the targets for the reconstruction in the shape model, they have done that and then used anthropometric data and metadata in regression to estimate the PC weights. So you can use their model and just take the age, sex, height, and a few scalar measures that you could acquire with a ruler to get the PC weights to drive the reconstruction. So you don't need any 3D mocap or 2D mocap to give you like spatial locations. You can do this with scalars. So this is super helpful because otherwise, how do you get the position of the landmarks unless you have an optical system or a magnetic system to track it? So this will really help people who don't have access to those instruments or don't want to use them for whatever reason. Okay, so you get bones, but by themselves, that's not actually a system, right? You got to do something with them other than look at them. So here's a tool, very reliable. I mean, that was his goal. Produced by Luca Modenese and colleagues. Started this work early, but publication took a long time, so 2021 until it came out. You can get this tool on Luca's GitHub page, Modenax. I can download it and start using it later this afternoon. This is a great tool. You feed it bones. Don't matter where they come from. Could come from your labor by manual segmentation. They could come from a database, shape models. It doesn't matter. It's agnostic to that. You feed it bones, and through geometric analyses, it's going to automatically identify the relevant landmarks that will allow you to build the coordinate systems and assemble a topology that articulates and have this ready and printed for OpenSim. It's automated and it's quite reliable. That's one of the good things about Luca's technology, is it always works, which you can't always say about software. So even if you don't use this, check it out, because there's tools like in the geometric analysis that are useful. So if you need to do geometric analysis for surgical planning and implant placement and stuff like that, that is relevant to these bones, maybe even not these bones, have a look at how it's done. It's quite robust. So they're able to identify all these landmarks and use that as the basis for establishing an OpenSim model that's personalized to that bone geometry.
Is this open source?
Open source, yeah. This is MATLAB code, yeah. So you can grab you can clone the repository, and start tinkering to your heart's content. It's great stuff.
Is that the whole body or just lower limb?
Just lower limb. Yeah, pelvis down. Now you can assemble a Franken model by jamming a torso on top of it if you like. But it doesn't personalize those features, but you can add to it.
So what if there are implants?
Well, if there's implants, you now have at least the skeletal model, and then it's up to you to interface the two. And in addition to the model, if it's relevant, you get these landmarks automatically. These are, femur head, the tibial plateau, femoral condyles, and the ankle. Why might that be useful? Well, let's go to this next part. So you've got an assembled model now, automated, rapid, and you don't need to labor over any type of manual assembly. Okay, but one of the drawbacks you could say about that tool, which has got the acronym STAPLE, the previous tool, is that it will personalize the orientation of the coordinate systems and assemble a topology, but the mechanisms of the joint is not itself personalized. So if we focus in on the joints now at the next stage, we can represent how the joints move from very simple idealized joints like hinges or revolute joints through to more complicated ones. And the hip is actually pretty close to a ball and socket if it's healthy and intact. That's not a bad simplification. That's pretty good. And if you get certain types of knee replacements, yeah, it starts to get hinge-like, but the natural knee is definitely not a hinge. And the ankle, as much as it pains me to say, is also not a hinge. It's not a Kleenex box attached to your shank, just swinging around. It's quite complicated. Now we do have some capabilities in that. Jayashni Maharaj is a research fellow with our team who's done a lot of work. She's a podiatrist originally, but has focused a lot of her work on foot biomechanics. She did her PhD with the UQ team, Glenn Litchwark and Luke Kelly and Eddie Cresswell. So they have excellent capabilities in the foot. But I'm going to focus a little bit in on the knee because it's probably the biggest violator of the assumption about ideal joint motion. Now, yeah, the anatomy, if you've got your cruciate ligaments that are crossed and assume that they're well and truly stuck onto the bones and not moving anywhere, that naturally forms like a 4-bar mechanism. Now, and that's not a new idea. That's from some German guys in the middle of World War I. So for a long time, people have appreciated that the knee, if you view it from the sagittal plane, looks like a lot of parallel mechanisms that are studied in mechanical engineering that have nothing to do with the knees per se. Main problem with this assumption is that the ligaments are not isometric in reality, right? They're not an actual steel bar that doesn't extend. They do strain. We know that as you cycle the knee, and if you implant a gauge, you'll see that different ligaments undergo stretch and relaxation at different times, and even bundles within them have variable strain. So since that very early or initial look at the knee, there's been a lot of development in that area. So this approach that we'll talk about here, I don't know if it's fair to say it's first, but at least popularized by some of the Italian groups, Sanchisi and colleagues in 2009, and then another Italian who worked with our group, who you guys may know, Martina Barzan. Her PhD work was on how to create these, how to personalize them, how to validate them, and so forth. And she developed, this is an image from one of her publications, mechanisms with minimally extensible ligaments. So we allow the ligaments to potentially or to elongate in small amounts and predict the motion of the knee just from its geometry alone. So the natural question is, the unfortunate thing about Martina's process, I should say, is that it was very laborious. She processed it all herself. It involved extensive optimization because it's very, very stiff numerically to get that system to work. And that's a very painful thing to do. So our question is, maybe we could automate this process, because the inputs to her model can be derived from the staple tool, from geometric analysis and potentially some template fitting. We can get all the inputs we need into that mechanism automatically. So we can go from medical imaging automatically through to the middle point to that model here. Now, the question we don't know the answer to is it accurate if you do this all automatically? And how does it perform more generally? Like, can you do that? Do you need, will it work? Will you need optimization? How fast will it perform? And many other considerations. So this is work that Beijing Shi, he's a PhD student working in the CMIT team, and he's working on this, and he's got a all-star cast helping him here with Martina Barzan, Azadeh Nasiri, and Jayashni Maharaj, who will help him get over the line and get that work done. But this is his second study of his PhD. He's going to take the data that Martina developed in her thesis, and her process is the bottom line. She manually processed it, identified all these sites, created these models, and this is the kinematics predicted from her models. And it's been validated against experimental measures of the same people at 4 different postures within the MRI. Now, the limitation on that is the bore size on the MRI is not big, right? So you can't flex your knee very much. So the model can predict kinematics out to considerable degrees of flexion that you can't access through direct measurement. So we've also added in the cadaveric data. It's not the same people, but we have we have what we would expect from cadaver motions as well. So we're going to try the top path. We're going to automate this whole pathway and see how well our automation performs both against those measurements and the previous manually created models as well. And we'll also characterize any performance improvements like speed. Because we're after this, if this takes 20 hours or 3 days, this is maybe not going to work so well for our purposes. Okay, so just to review where we're at. Get into the section where it's more hazy, where what you should do maybe is not so obvious. Currently, you can go from low to high fidelity measurements, and you can either create your own brand new model by hand if you were so inclined, but much more likely you're going to do some combination of deforming a template, either a statistical one and or with some type of more complex deformation tapped on top of that. And then you can assemble it automatically through Staple, which is that tool that Lucas made available. Or again, if you're a glutton for punishment, you can assemble it in something like NMS Builder, which gives you a lot of freedom, but it's very manual. And then you're left with a personalized skeletal model that has generic mechanisms for how the joints move, which you can further refine by attaching, say, for example, the knee, this type of closure mechanism to the inputs from the previous steps. And then if you get to this stage, this last box, you've got personalized skeleton, personalized mechanisms. What do you do with the thing that actuates it all, the muscle? That's a big problem, like a legitimate problem. Still, this is more or less, this is getting towards the end of its life. Like, I don't know how, at the rigid body level, what further improvements are going to be made other than performance. Maybe other joints, moving to the upper body, more complicated joints, certainly. But let's say down here, it's getting pretty complete. This is tibiofemoral and patellofemoral, I should add as well. What do we do about muscle? This is nowhere near complete. This is really pretty hairy. So let's jump over and look at the muscle now. So on our left, this is someone who's had their semitendinosus and gracilis harvested for ACL reconstruction. And you can see the muscles here on the right are traumatically affected by that harvesting process. They're all shrunk and retracted, and these are this is the way it should look. This is a normal set of muscles. Now, this is just two, but you can imagine all the other ones around the leg. these are real volumes with curvature and complicated shapes. And that on the right, that really doesn't look like that, which is a problem, as we were talking about earlier, right? If it really doesn't look like it, it's probably not it. The other is not always true. You can trick yourself into saying it looks like it, but if it obviously is not right, it's definitely not right. So, but it's a simplification that we had to make. I mean, how else are you going to resolve the force generating capability muscle computationally? It's very difficult otherwise. So first thing you can do, I should just jump back, is if we just park the problems with this for a second and say, well, what can we do right away to make the line model better before we throw it out the window entirely? What are the steps we can do right now based on established literature that would make it better? So the first thing you do is, once you've been through the skeletal pipeline, your model's been adjusted, it's changed size and so forth. So first you can implement this algorithm, and this is also freely available on that same GitHub page. So I'm doing a lot of marketing for Luca right now, but he's now back in Australia, which is absolutely fantastic for the biomechanics community here. So in this instance, what this algorithm sets out to do is ensure that the muscle fiber and tendon operating ranges are preserved even when you change the size of a model from a template to the individual. Now, why that's important is when you go through any type of transformation, whether it's linear or otherwise, the relationships between the dimensionless tendon and muscle fiber operating ranges are not preserved. So what that means is if I change the length of the muscle, because I've scaled the bodies that it attaches to, for at a given joint angle, I'm not going to necessarily be in the same position on these curves. And you say, well, why is that a problem? Because the literature indicates that, in fact, these curves are preserved largely across people of very different size scales. So if me and Dale are both with our knees at 90 degrees and the other joints more or less in the same posture, we should both have our quad muscles operating in roughly the same place on the operating curves. When you scale a model, that's not ensured. That's nothing about the scaling process that preserves that. So with this algorithm, and it's outlined in this paper, and like I said, you can access the code. What this does is it searches for a new optimal fiber length and a new tendon slack length, which will best preserve these dimensionless curves from the template to the individual. So what that eliminates is cases where for normal physiological motion, your muscle operates at an artificially short or artificially long length. And if that's present, you're going to either have very, very high passive forces if it's at a long length, or you'll struggle to generate force because it's artificially short, even though you're within the physiological range. So this is a step you can take if you find in your models that you do get a lot of passive force development. This is something you could look at to address that problem. It's not going to make it worse, like I tell you that. It may not fix it, but it will diminish the problem. Okay, so that's still within the line actuator modeling approach. What about muscle strength? So you could process the MRI again, segment out all the individual muscles, and if you think bones are bad, it's worse for muscles because there's more of them and their borders are not as clear in many MRIs, as you guys probably appreciate. But luckily, Jeff Hansfield and his team, when he was doing his work with Professor Blemker in the US, they've made our lives much better from their efforts. They took a number of cadavers, I think it was in the range of 30 or more, I believe, across the age range, both sexes and so forth, segmented out all the muscles, and then amazingly, actually very non-intuitively, were able to show that based on just your height and mass, no factor for sex or anything like that, or age, just based on your height and mass, this regression equation describes about 90% of the volume variation, which is weird. have to say. But it's good because what it means is for normal people, probably not athletes, probably not pathological cases, but like your normal folk, this will get you the total volume of the lower limb muscles. So this regression equation predicts the integrated volume of all the different muscles. Then they've kindly also provided the fractional assignments. So you can then break the total volume into the individual muscle. And then if you know the specific muscle stress, which is a literature value, the optimal fiber length, the volume of the muscle, and also the length of the optimal fiber length, this reduces to the cross-sectional area. And now you have an estimate of the muscle force. So you can, the maximum isometric force, so the maximum force a muscle can produce when activated and at optimal length. So this process is also codified. I neglected to drop the web address for the GitHub account, but if you guys want it, just send me an email afterwards. I'll point you at it. So we have a script in MATLAB where you feed the height and mass of your person, and it will customize your models, all the muscles, scale factors accordingly.
How did they know they were optimal lengths in cadaver?
They didn't. So this is just, this assumption is that at optimal length, if this is the volume and you have the other parameters, this isn't the isometric force. So they don't have any direct validation of this equation. This is just the modeling assumption. Their work ends here. And so this is the implementation, for example, that in the Rajagopal model from 2016, that's how they've adjusted their strengths in the templates. And we'll follow suit. Now, if you wanted to do it on a person-by-person basis and this was not adequate for you, you could certainly do that. You could segment each muscle and get your own estimates that way. Okay, so that's the good news. You know, you've got these two processes that are automated code, which will improve the way that the muscle behaves and make them more personalized. The bad news is when you go to line actuator models, even when you've got personalized joints and all this stuff, these types of things can happen. So this is work by Bryce Killen, who was a PhD student at GCORE, and he's now gone on to a fellowship at KU Leuven with Professor Yonkers. And he's pointing out that your muscle definitely doesn't slice through your bone. It doesn't make right turns and switchbacks. And so there's a bunch of things that happen as a function of how a line actuator is implemented in a model that are clearly wrong. And, you know, we're probably the type of people who are bothered by this type of thing. Other people aren't, they don't care, or they might not even know it's a problem. So that's visually wrong. And then this is a consequence of some of these things. Not this, the interpenetration is not observed here, but when a model, when a muscle interacts with, say, a wrapping object or a conditional path point or something like that, you get these types of things like staircase effects in the lengths. Now, you know, apart from that also not being real, the consequence of that is a very rapid change in the length. So the velocity of the fiber or the muscle fluctuates a lot, which if you're using a hill type muscle model to derive force and you get a big velocity change, you're either going to get the force drop to zero, or if it's a lengthening contraction, the force will go very high. So neither of those things are good for you. You know, it becomes a real problem. And this is persistent in the lengths and the moment arms and so forth. So our approach, or Bryce's approach, was maybe we can just solve this with some type of massive optimization. So what he first identified was, what are the problems? So he could quantify the penetration of a muscle into the bone with basically a ray intersection technique, and he could identify it and put a penalty on it when it happened. he could identify what are called polarity errors. So you see this dashed line, that's the 0 point for the moment arm. And in some modeling cases, you've got a positive moment arm, and the literature says that it's a negative. So this is a big problem because it means the muscle's function is inverted, at least in the model's case. Smoothness as well can be defined mathematically, and gradient error. So that means one line the slope should be negative, and the other line, the slope's positive, whereas they should both be doing the same thing. So these were the host of errors. And the approach in this paper was, well, if I adjust the size, the position, the orientation of all the wrap objects and via points, and I treat those as design variables, can I get all of these bad things to go away or minimize them? And he used a big supercomputer to try and do this, because you can imagine it's a lot of parameters to try and handle. And it sort of worked. It won't make it worse, and depending on the muscle and the problem, it can work as well as about 80 or 90%. So that means out of them, let's say you had 100 muscles, it might work for 90 of them. But in many cases, we're not able to eliminate these features. And I was saying earlier, maybe it's because the way we approached the optimization was not good enough. Maybe teams or groups that were specialists in that area could have done a better job. Potentially, I don't rule that out, but I think there's fundamental problems with using line actuators to represent muscle that are never going to go away. Maybe never strong, but are going to be really difficult to get rid of. So that's where I wanted to end with what we know well for sure. We're thinking now to potentially abandon the optimization of the line actuators and just say, well, muscle's a volume. Why don't we just model it as a volume? Like, we're making it too difficult for ourselves to reduce a 3D shape to this line path and expect it to be well behaved. Like, it's just an unrealistic expectation. So benefits, well, muscle is a 3D object. So we have like reality on our side, which is very good. You want it on your side, right? It also changes shape. Lines don't really change shape, not in the way muscles, 3D objects change shape. And if you have a 3D object and the muscle representation is also 3D, well, now you have like obvious targets for the personalization. If you have a big volume of muscle and you've got a line, what am I supposed to personalize in the line? Like, what am I aiming at? So when it is a volume, the targets are obvious. What's the problem? Well, it's really difficult, right? I don't know if you guys have looked at the papers that do complex like FE analysis on muscle. It's a nightmare, right? It's really difficult. It's super time consuming. So if we thought optimizing muscle paths was bad, this will be horrendous. And yeah, okay, the targets for personalization are obvious, but how you implement it is like non-trivial. That's a big problem. Okay, so if we go down this path, these are the questions we want to know. Is it going to give us physical, so like muscle not cutting through bones and other muscles, and physiological, no right turns and no rapid fluctuations in the kinematics? Is it going to give us realistic muscle tendon unit kinematics? Because if it doesn't, it's not useful. Can we personalize it? And will the resulting kinematics be valid? And then if the first two are met, we can look at the last one. So can we automate this and can we do it fast? Because there's no point doing the third, right, if the first two are wrong. So that's the sequence that we're looking at here. So we mentioned the finite element approach to it, right? But there's another group or study or fields that have been doing this for a totally different reason, which is the gaming and entertainment industry. And everyone chuckles, but they're way ahead of us. They are absolutely beating the pants off us in this because they got a lot more money. And their approach is they're not interested in the physics or the energetics. They care if it looks good, the aesthetic, right? Is it convincing when they make an animated figure that's moving? Do you believe? Because we have a pretty good intuitive sense of how muscles should look because we're looking at them all the time. They're approaching it aesthetically. And they've been doing this for a while, maybe not quite as long as biomechanists, but their rate of progress is way higher than us. And they're starting originally with like these primitive muscles that were like analytical shapes, ellipsoids and weird things like that. And they imposed some really simple constraints on them, like the incompressibility and things like that. And they got them sort of working, but they don't validate them in the way we do because their imperatives are very different from biomechanics or medical devices. They just want to get it looking good. That's their validation. And these primitives or these early attempts had no dynamics. There was no activation. The muscle was not contracting. It was just moving. It was kinematically driven because it was attached to the skeleton. Now, since then, those things have evolved a lot. Like, I mean, if you look at the bicep here, and then you look at the arm here, this is a massive jump, right, in realism. And now the animation sphere or area is starting to get closer. I don't know if it'll actually merge or if it'll bounce off of you, but it's getting closer. And now a lot of the animation software use finite volume or finite element methods, simplified ones, but they use that technology or those methods to help them deform their models. And increasingly, they include activation, so you can actually kind of contract the muscle, or at least simulate the contraction. But again, validation is not there. If you look at those papers, they blow you away, but you keep reading and reading and reading, and hope they're going to show you like a comparison with the measurement, and it's just never there. So, what's the trend here? So nowadays, this personalized morphology is assumed. That's pretty much always going to be there. So it'll be customized from something. It won't be just an arbitrary shape. These tools can now be used to try and characterize, like to do system identification, passive and active properties, like stiffness and things like that. What's really cool is they're also being coupled to biophysical models. So trying to relate the mechanics to biological processes by which muscle grows or deteriorates and things like that. But again, nobody bothered to validate the thing. So what we're proposing is to do the simplest validation possible. We thought we would start with the lowest hanging fruit. And we're going to use something called the Ziva Dynamics, which has just been acquired by Unity. I don't know if you guys know what that is, but that's a gaming environment or engine that can do real-time immersive environments and augmented reality. So they haven't integrated it yet. You still have to run this through like Mayavi Autodesk, but that's what's happening. It's going into Unity. And this is an example of one of their models rigged up. So it uses the animation lingo. So instead of a model, it's a rig underneath it. And this system can actually be deformed. So our approach will be to use MRI, undergo some type of morphing of the skeletal system, and then apply that to the Ziva Dynamics model and see what happens to the muscles, and also impose secondarily a muscle deformation to try and get it to match the static posture in an MRI. That would be our first goal, just to control the software the way we want. And then we're going to move in the lab, the same person that was in the MRI space, to a large range of motion and measure at different static postures using 3D freehand ultrasound. We're going to try and reconstruct the muscle and see if we can get this model to deform to match all of the subsequent postures. So it'll be passive, no contraction dynamics going on, just the arm or the leg moved to different postures, and see if we can validate how this deforms passively. Quantitative validation is what we're going to try to do. But we've never done it. And I imagine there's going to be some problems. So that's actually where I wanted to end this conversation, because it's going for a while, and get your guys' feedback, thoughts, really on the whole thing, but I think especially on this new area of how to do the muscle model. But also thank you for listening.
Thanks.
Not do muscle contraction in the MRI instead of using ultrasound, then you can get the full body, much better definition. Could ask them to maybe flex, plantar flex, dorsiflex, or even.
Yeah, if we had if we look at the calf and we get a non-ferrous rig or something like that, we could probably try to do some contractions, which have been done, but they're really low intensity contractions usually because the acquisition time on the MRIs is long. But there may be ways to do that. I hadn't really given that much thought. That's a very good idea.
Getting some spring, well, it's difficult to put metal springs on there. Something that maybe even a polymer material that you can change the stiffness and ask the guy to step it into a certain value, so you actually know exactly what load you are.
Yeah, actually, that would be much better too. Because that would be good.
Then you can at least you got the load as well.
Yeah, or we could ask the companies to get us one of those big bores they use for like horses, MRI horses or something.
It's one of the best school.
Yeah,
I don't know
that's
whether
right.
the human wants to
They
go.
maybe won't put us in there yet.
I have to leave for another meeting, but I'm sure there are lots of questions, and for those who can stay, please fire away. And right, but I really appreciate it. Fantastic talk. It's a nice overview. I think many questions we have, and we'll keep talking.
Absolutely.
And then
Well, if I don't see you today, I'll see you at the end.
Right. Okay.
Cheers. Yeah, so do you think this is like a crazy idea? Okay. That's what I wanted to check.
I had a question. How does that ultrasound probe, what's it actually measuring, and how's it going to measure the depth? Was it the 3D kinematics of the muscle, technically?
Yeah, well, so we would have a motor-driven dynamometer, so it moved them to an angle and then hold them static. And then the freehand ultrasound, we had a question of course, which muscles to try and image. So we wanted to do the quads because logically, like you start flexed and you go extended and you go fully flexed, they're going to stretch and they should change shape a lot. And they're accessible because they're on the top surface and you don't have to get the person in a funny posture, but they're really big. So when we were reviewing this, we said, like, I don't know if we can image them with 3D freehand, because the way it works is you do sweeps and it's acquiring at like 50 hertz, and then you go and process each image, and you can, because the ultrasound has a probe, has a coordinate frame attached to it, so you can project the 2D frame into 3D and eventually stitch all the slices into a volume, but it's like not easy at all. So we said maybe if we do kids, because they're small, we could still do the quad, but we would do a child model, so like it would be less difficult to implement. That was one idea we had. I think we probably will to the kids, just like it'll be way easier than the adult.
I had a question about whether there's another step they could do in parallel to this.
Oh yeah.
So I think doing validation of sort of gaming approach to things would be really cool. Maybe they'll even get interested in some sort of licensing or something. So I'm sure that's going to be great. But going back to that problem with the line segments, basically starting to go into your bones and things. Perhaps there's a step here where you actually do a statistical shape model of the muscles that you're segmenting, and then if you then you have an idea of force, then could you just use volume conservation constraints on a statistical shape model generated muscle organization?
Yeah, maybe.
To then basically gives you the constraints you need for your optimization algorithms to do that.
Quite possibly.
Yeah.
We'd have to like sit down and try and hash out, because this system, Ziva, does sort of a low rank FEM approach for its muscle deformation that does things like volume conservation of the muscle, rigid attachments to the bones and a few other things. So, but maybe there's an even cheaper way to do it that doesn't involve.
Yeah, I think you want to do both. Like one is, having even MRI images of the muscle groups in different postures, and then just visualizing what shapes do they take.
Yeah.
And does it conserve volume? That's a fundamental question you could ask and answer with that kind of MRI data. And then you just use that on your line models, because in the end, these 3D models, they're still, if you're going to model the full contraction of all the muscle fibers in a three-dimensional sense, it's going to be computationally and more. It's going to be more taxing.
Yeah, we wouldn't. So we wanted to first just get the passive kinematics of the muscle.
Yeah.
And then use that to drive still a hill type muscle model.
Yeah.
So we would have like a low dimensional force model.
Yeah.
But the kinematics would come from a volumetric deformation.
Right. So I wonder then if what you need first, what would be great is to just do like volume measurements and shape measurements.
Yeah, we just got to be able to get those the measurements from the different postures. That's MRI is great, but we've got the issues with the size, and then the ultrasound. You don't have the issues about mobility, but now you have the problem of processing it and actually being able to measure it with the freehand technique.
Have you considered measuring the external? So when you contract muscles, the external shape also changes.
Yeah.
I think you won't get in as much information as you would get from ultrasound. So you don't get anything internal.
Yeah.
Would that add any value? Because externally you probably can measure in real time, or it's quite fast with projecting a pattern of sound, or actually is 3-dimensional digital image correlation.
Yeah, like spectral tracking.
Yes.
I thought of that. That's a good idea too.
I think they do that in gaming, right? They put a
Yeah. We do when we do like mechanical testing. We like spray paint with like droplets. Track that. That's a good idea.
I've seen someone at start on the car.
Yeah.
And not this was the application. They were looking at the stumps for amputees.
Oh, okay.
So they were measuring using digital image correlation, measuring the shape of the residual layer.
I think that those are all I made. I'm actually going to write them down. So I think my memory is not great. So just drop in the notes. So that's a fantastic idea. Speckle tracking. Good idea. That was worth the trip.
I suppose you know that the really small retroflected markers you can get sort of hemispheres of a few millimeters. I mean, it'd be awkward to cover someone completely with those, but at least to live on the key areas. I mean, to
do the old school biomechanics where they have to do the motion capture in the nude. So the early tests were done like that. Yeah. And in the dark, because they had the optical systems that would like flash the light. Maybe in Germany.
You showed a slide with where I think muscle volume was related to height and mass.
Yep.
The weird one.
Yeah.
That was a bit surprising.
Yeah, it is, right?
That,
check out this. This is a great paper.
Because people have different amounts of fat.
Yeah.
Like if you look at caloric, some have really thick layers of fat. And so I would have expected so some of that mass in some people will be purely muscle, some people it will be a lot of fat.
Yeah.
But it doesn't seem to have affected this much.
Well, this is 33 cadavers. So look, most people who die are old, but not all, unfortunately. And I don't know if they had really a detailed history of each of the cadaver, like what was their occupation, did they play sports, all those types of things. So, and I don't know if they chose their cadavers from an available set to yield this 33. That I don't know, but I agree. Everyone is always surprised when you look at the quality of that regression. That stands out.
It's amazing that they're able to get the sort of coverage of ages, because getting young cadaver tissues
is uncommon. But I had cadavers, I think, of specimens as young as 10 that study.
Yeah, it's amazing.
Right through to very much older. Yeah, but it it works quite well. So this one, like I mentioned earlier, if any of you guys are interested in the toolboxes but can't access them or anything, just drop a line. We'll point you at them. But
with the modern 80 Lucas toolbox, one of the steps we were talking about is registering the bones or putting the bones together essentially to make joints. So that looks like it would be good for some joints, but other joints that move and have sort of characteristic motion. I mean the joint positions will depend on kinematics and other factors. So it's essentially this sort of getting it into a sort of getting the articulations together so that you have a moving representation of the joint.
Well, I mean, I don't want to put words in Lucas' mouth for him or anything like that, misrepresent his intentions in this. But one of the benefits of this is those bones can come from totally different sets if you are so inclined, because, or from successive MRIs, et cetera. So the main benefit is that if you know you want to use these geometries within, let's say, the OpenSim modeling environment, this tool will do that assembly and customization for you and automatically print the OSIM file so you can load it in and hit the ground running for kinematics and inverse dynamics. But you're right, many joints, like those joints will not necessarily contain the sophistication that you might be after, especially if you know there's something abnormal going on there, or if it requires further modification, or it needs an implant, like some people were bringing up earlier. But it will give you like a really solid base from which you can then further modify it if you need to.
Yeah, I had a question on the freeform deformation. My understanding, when we're doing the shape modeling, it already does that as part of the pipeline. We're taking a host mesh and fitting it onto our training set.
Yeah.
I mean, I don't know how you would build your consistent mesh amongst your training set and then do the PCA any other way.
You're right. So there is a deformation step there, but if it's using Gaius, that's like a radial basis function deformation, which if you evaluate the fit is quite good. So I don't think there's any problems with that. The difference is when you go, let me jump back here. This can be much more localized. So for example, in this case, we apply the freeform deformation only at the proximal and distal ends, because we had high resolution joint scans, but we didn't have any information in the middle. So we used the shape modeling initially, statistical shape modeling, to give us a pretty good approximation. And then in this case, these were people with FAI. So we know they had funny shaped femoral heads. So we used the manual segmentations from the joint specific scans, and then the host mesh twisted and did slight deformations at the top and the bottom of the femur, and also in the acetabulum, that were not within the training set, because the training set was healthy individuals. So it was like, if you reckon that your population is pretty close to normal but has something unusual in one location, and you say, oh, well, I'll use a shape model to build what would be a typical representation for this person, and then I'm going to add or customize one aspect or one feature. That was the value here. So like if you had a knee replacement, you could use a shape model and then bolt on the replacement, something like that.
No.
Right, any other questions at all?
Well, thanks.
So,
Yeah, go ahead.
So with that kind of method, you are saying that even though you, for the shape model, the training set is quite healthy, then because if we are talking about like joint replacement, the patients are usually with unhealthy joint shape. So with that method you are saying, okay, we already have a healthy training set, then we can combine with the post-mesh fitting to fit the statistical shape model to the
Exactly.
health.
So you could, instead of having to acquire a full lower limb MRI and process it, you could use just like their height, weight, and a few scalar measures to get the rest of their skeleton. And then if you had a knee specific MRI or CT or the CAD of the implant, bang, you can attach it. Or if you're looking preoperatively, you could deform the knee bones to match your preoperative imaging. Yeah, so you can fuse the methods. I think that's the value there. So they're normal except for that one spot.
Yeah.
Yeah.
Okay, well, no other questions. I think we might finish up, and please join me in thanking David again. for
My
his-
pleasure. Thank you very much, guys. Thank you.
When are we sending that staple thing out to everybody? That Lucas